In this video, we're going to explore what's called retrosynthesis. What is retrosynthesis, you ask? The name implies that it is a retro, which is backwards, synthesis. It's an analysis of a reaction sequence, but we're starting at the end. We call the end of the sequence the target molecule. In research, particularly pharmaceutical research, drugs are found in various sources such as nature, and these drugs are found in very small amounts, and they screen towards a disease, and they're positive in their potential, and they have to be made in higher quantities so we can begin trials, but we don't have enough of this drug to start trials. So you hand over the structure of the molecule to an organic chemist, and they will come up with a synthesis of the desired target. So to make a long story short, retrosynthesis begins at the end of a synthesis and gives us a target that we must make from smaller molecules by using reactions that we have learned. So we have a new question. What reaction should I know from my first retrosynthetic analysis? I'm going to boil it down to 5 key reactions that we've studied in Chapter 7. The first one involves making carbon-carbon bonds. That is the crux of synthesis. We can start with acetylene if this R group is a hydrogen, or an already terminal alkyne where R is a carbon group. In our previous video, we explored 4 bases that could do this job with high yield, and we generated an acetylide ion, which was a nucleophile. After generation of the nucleophile, we reacted it in an SN2 reaction with a carbon that had a leaving group. Our first encounter with leaving group was simple halogens starting chlorine, bromine, and iodine, and that was the electrophile for this reaction. The new carbon-carbon bond is this bond right here, and we did our synthesis to make this internal alkyne. I'd like to point out it wouldn't be internal if our R was H, it would be a new terminal alkyne. But the fact is, we know how to make this bond. The other 4 reactions are manipulations of alkynes towards functional groups in this course. We learned how to make a terminal alkyne into a ketone using mercury sulfate, sulfuric acid, and water in a hydration reaction. We learned how to make a similar terminal alkyne into an aldehyde using disec-isoamyl borane in step 1 and hydrogen peroxide, sodium hydroxide in step 2 to make an aldehyde. Aldehyde right here. We also learned how to take internal alkynes and reduce them using hydrogen with this combination down here called Lindlar's catalyst, or hydroboration and protonolysis. Both of those sets of chemicals resulted in a cis-alkene, here with the H's here. We don't need to show the H's. There's a cis-alkene. And equally valuable was to make a transalkene, and to do so we needed an internal alkyne with sodium metal and ammonia solvent and proton source, and the blue H's come from the ammonia to make a transalkene. So let's do our first retrosynthetic analyses. We'll start with one of these 2 targets, either a ketone or an aldehyde, and go from there. On your test, you will be given a target molecule, in this case clearly a ketone, and it starts off like this, and it states that you are allowed to start with these materials for your forward synthesis. That's acetylene, also known as ethyne, and alkyl halides of 5 carbons or less. So what we have here is a target molecule, a ketone. We have to go back in our memory banks. This is all in our memory up here, this whole area. And won't be given this on the test. And we hunt down our recollection of how to make a ketone, and we say, here's a ketone. How did I make that ketone? I made it from a terminal alkyne. If you look carefully, there's R. There's a carbon off of R, the alkyne carbon, and the second alkyne carbon. And in the end, same carbons are there. R, the carbon off of R, and one more away from that. That means that this target molecule came from an alkyne, where the alkyne used to be these two carbons down here. So we have a 5-carbon chain with the alkyne on the carbons 1 and 2. Can be made into this ketone, and we can finally answer this question: what does this funny looking arrow mean? And what it means is, I know how to make this molecule at the top of this target. I know how to make that target from this species here. Let me put that in writing. So the arrow means that I know how to make the molecule above the arrow, before the arrow, from the molecule below, or after the arrow. Which in effect means this is our new target molecule. And how do I make alkynes from simpler molecules? Here's a alkyne that came from 2 simpler molecules here and here. So the bond I know how to make is this bond between 2 and 3 right here. It comes from this anion, always an acetylide ion as the nucleophile, which you don't have to identify in the test, so I'm not going to put it there. But it is the nucleophile. And the carbon with the leaving group would be carbons 3, 4, 5 with a methyl off of there. I'm going to sneak in carbon 2, but it won't be carbon 2 here. It'll be a halogen, such as a bromine. Those 2 pieces will react to make the molecule before this arrow. This species being called acetylide. This species being called 1-bromo-2-methyl propane. Now I have 2 targets. Where did this come from? And well, typically I'd ask where that came from, but I see that that molecule is actually on my list. It is an alkyl halide of 4 carbons, which is less than 5. So I don't have to account for that. You'll see on tests where you do have to account for that by making this from an alcohol, but on the same tests you'll see reactions given to you where I tell you how to make the alkyl bromide from an alcohol. We're not going to do that on this sample here. So we're done with those 4 carbons. And this comes from acetylene, which is this. And that would be the end of this retrosynthetic analysis, with the molecules that we're allowed to start with being circled. In our forward synthesis, which you must also do, outline a forward synthesis. Part 2 is to outline a forward synthesis of the target molecule. I fixed a typo here. How do I make acetylene into acetylide? That would be taking us from here to here. And one of 4 bases is good. KH is a simple one. Not a lot of writing needed. Hydride, very strong base. What molecule must I add to acetylide, which is now here, to make it into this new target here? And the question is, the answer is, sorry, you need to use this molecule right here. ChemDraw does its own thing sometimes. And then the question is, how do you take your terminal alkyne and make it into your ketone target molecule? And the answers can be stolen from above on the screen. This is the oxymercuration proteinolysis protocol as found in section 7.5a, and that gives us a ketone. If my target had been an aldehyde, with the carbonyl on carbon 1 and carbon 2 being a CH2, the only thing in this synthesis that would change would be the very last step, and we could make the aldehyde using these chemicals here. Let's look at one more target molecule that exploits one of these two reactions before we call this video quits. I have another target over here. It's a transalkene. On the test, it would most likely be drawn like this. I really have not changed anything. And the question is, how do I make a transalkene? And I look in my arsenal up here and I see the only transalkene I know how to make so far is by reacting an internal alkyne with sodium and ammonia. And please keep in mind, all the carbons here in the transalkene are accounted for in the internal alkyne. Same number of carbons. So this is not going to look pretty at first, but basically that comes from the alkyne like that. And there it looks a lot better. Same number of carbons as indicated here. This states that E2-methyl-4-octene can be made from 2-methyl-4-octine. Now the question is, where does this molecule come from? Well, we know how to make this bond or this bond, and it doesn't matter which one you show me how to make first, which would be last in the synthesis if you're thinking backwards. That piece comes from the anion being on the acetylide. In our synthesis, we're always using an acetylide, and we're always attacking a carbon that has a halogen on it. That is not carbon 5 over there. That is a halogen, such as chlorine. The combination of these two things would make this target above. I circled the 3-carbon halogen-containing species because it's on my list. And here's an acetylide. And the question is, where did that acetylide come from? Quite simply, this acetylide came from the same molecule, but it had its H. So it wasn't an anion. Now the question is, where did this molecule come from? Well, that's a carbon-carbon bond that I know how to make right there. And I believe we've already made this species before. It is identical here to this species over here. So I'll tell you where this came from. It came from these two things. Let me just grab them. The bond between 3 and 4 was made by acetylide attacking carbon 3 in isobutyl bromide, and acetylide, which is this species here, came from acetylene, which is this species here. I'll bring it over, and we'll have a retro arrow right here. And that's the end of the retrosynthetic analysis. All the circled boxes account for all of our carbons. And the synthesis starts exactly the same as this one here, except we don't do that last step. We're not making a ketone. We're just stealing this over here. And we're at this stage right here. We need to make this into the anion up here. So I'll show that in my next step. I moved things around a little bit while you were not watching. We left off here, and we needed to make that into an anion here so that we could do this synthesis step. We're not ready for the synthesis step here because I don't have my anion yet. And the question is, how do I make the anion? And the answer is the same as before. Strong base such as KH. And then we're going to mix in what with this to make this here? It's a very good question. The question is how to make this anion into this species here, where there's a new carbon-carbon bond between that carbon on the left, which used to be a nucleophile, and the carbon on the right. To make it an electrophile, we need to have a halogen on it, and the answer to the question is this right here. Propyl chloride does the trick. And now we are on our way to our target. We're going to make this into our target up there. I just rewrote the target symbol here. How do we make this internal alkyne into a transalkene? The only way we learned how to do that was up here using sodium and ammonia. So that is the answer to how to finish off this second retrosynthetic analysis. So I hope you have found this video on retrosynthesis to be useful, and I look forward to our next video.